In the standard 15 class notes, we're going to continue our look at finding the zeros of polynomials, which we just kind of introduced at the end of the video notes. But one thing I'll draw your attention to here is the wording of standard 15. It says find all real and complex zeros of polynomials. So this video is going to focus in large part on this idea of complex zeros. But first, we're just going to kind of do a repeat of the way we ended the video notes by looking at this polynomial and just applying what we learned there. So this would be a good one to try on your own. Try to find all the zeros of this polynomial that we have in front of us based on what you learned in the last one. All right, so what we remember here is that we want to start by using technology. There is actually a lot of really interesting algebraic theory behind how to find the zeros of polynomials, but that's just not something we have a lot of time for in this class. So what we're always going to do is start by graphing our function and then finding at least our first 0 or 2 graphically. Oops, I think I probably want a plus sign in there, don't I? There we go. And then minus 20x squared minus x plus 21. Okay, and we'll go ahead and graph that. All right, and so here's the picture that we get here. And you can see that you can't get a fantastic view of this thing. One thing you could do if you want to kind of see the peaks and valleys of this graph is you can leave the x's alone, but just really change these y values quite a bit. So maybe instead I'll go like negative 200 to 200 and see if I like that view a little bit better. And yeah, I kind of like that view a little bit better. So what we're going to try to do here is find a nice zero, okay? Find a rational zero, okay? So rational just means can be expressed as a fraction. But really, you're just looking for something that's pretty nice. So we'll go ahead and look for a nice zero. Now, I'm kind of thinking this one right here is a nice one because it looks like it goes right through that tick mark, as opposed to this one over here looks like it barely misses the tick mark. And so if I had to guess, I would say that that second one is particularly a nice one. But you know what? I want to just go ahead and find this first zero here just so we can be sure. All right, so notice the zero is negative 6.14, it's saying. So that tells me that this is not the zero I want to pick as my starting one. So let's go ahead and find that next one that I suspected might be a nice one. Looks like it might be negative 1, but let's do the work to be sure about that. So get to the left, get to the right, and sure enough, it's negative 1. All right, so I'm going to go back here, and I'm just going to start by making the comment that according to the graph, x equals negative 1 is a 0. Now, one of the things you'll recall that we learned from the video notes is that, remember, C0 is a 0 of our polynomial if and only if x minus c is a factor of the polynomial. So anytime you find a 0, you've automatically found a factor. So the idea here is that I'm going to be able to take my polynomial, and instead of writing it like this, I'm going to be able to write it as x plus 1, right, or minus negative 1, times some other stuff here. And we want to figure out what that other stuff is. In other words, if you factor an x plus 1 out, what's left on the inside? And remember that the way we figure that out is to do synthetic division with the 0 we found. right? So we take all the coefficients that I see in the polynomial. So 1 for x to the fourth, 3 for x cubed, negative 20 for x squared, negative 1 for x, and 21 for the constant. Right? And then we perform that synthetic division that we learned about in the last video, right? So we start by dropping this one down. We multiply negative 1 times 1, which is negative 1. And then we add here, right? So 3 plus negative 1 is 2. Negative 1 times 2 is negative 2. We add there, so negative 22. Negative 1 times negative 22 is positive 22, so we get 21. And negative 1 times 21 is negative 21. And of course, when you add those, you get 0. Now remember, if you're suspecting that this here is a 0, you better end up with 0 here because this is your remainder, right? If you get something besides 0, either you've made an error in here or this wasn't one of your zeros to begin with. But then all this translates into the polynomial that's left after you factor out an x plus 1. So this one stands for x cubed. This is 2x squared. This is minus 22x, and then plus 21. All right. And so now we have a cubic. Now, we haven't really talked about how to solve cubics. We don't have an algorithm for that like we do for quadratics, right? We have the quadratic formula for that. So here is where we're still going to rely on technology, right? So now I'm going to type that in. And by the way, you could stick with this graph if you wanted to, okay? So I could go over here and, maybe I'm kind of thinking that that one on the right over there is, on the far right, is a nice one. So if I select that, okay, it looks like x equals 3 is a 0. However, I just want to make the statement that remember that polynomials can have zeros with a multiplicity bigger than 1, right? In other words, they repeat sometimes. Now, we know that if that happens, you'll see that behavior on the graph, right? So if you had a 0 with multiplicity 2, it should kind of look like a quadratic on that part of the graph. So while we know that, a fail-safe way to make sure you're not missing repeat zeros is rather than relying on the original to, let me just deselect this, rather than relying on the original to find that next 0, you could go ahead and put in that factored form that you just found, x cubed, excuse me, not the entire factored form, but what's left inside the parentheses. And then, if there was a repeat 0, it would show up again in this new polynomial. So let me go ahead and go back to Zoom Standard. Okay, and notice it looks like this one's crossing at x equals 3, just like we saw in the other graph. But just to be careful, it's not a terrible idea to kind of update your graph as you go along in these problems. All right, but I can definitely make the statement that x equals 3 is a 0. All right, let's move down here a bit. All right, so we're gonna, do the same thing. So, to skip down here a little bit, p of x is equal to, so I already have x plus 1 out there, and if x equals 3 is a 0, then I need to have x minus 3 as a factor as well. So the question is what goes in here? And again, we find out using synthetic division. So there's a 1 in front of the x cubed, a 2 in front of the x squared, minus 22 in front of the x, and a 21 as the constant. So put the 1 down, put a 3, and then that gives us 5 when we add. Then we get 15, which gets us negative 7 when we add, and then negative 21, which That's good. That gives us a 0. So that means this is x squared plus 5x minus 7. Now at this point, we know that this thing very well has zeros to offer. And in fact, we saw that there were 2 other zeros on that graph. But this is a quadratic. So we really don't need to do anything else with technology. Here we can just use the quadratic formula. Right? So to find the zeros of this thing, we'll just say x is equal to negative b plus or minus the square root of b squared minus 4 times a times c. And that's all over 2a. And so to simplify that, negative 5 plus or minus, that all simplifies to 53 under the square root over 2. And I always kind of like expressing my zeros this way. Okay. I like this because to kind of go back to the idea of quadratics that we studied in Standard 13, this thing actually is the h value or the x value of your vertex, and then you're adding or subtracting the same amount to get to the 2 different zeros, right? Because the idea is if you've got a quadratic, right, then if here is the vertex, then you should have to go an equal distance either way to get to a 0. So that's why I kind of like writing them like this. But if you left it this way, that'd be okay too. All right, but what does this mean? To kind of summarize, to list all the zeros, we would have x equals 3. We would have x equals negative 1. And then we have x equals, this is negative 5 halves plus the square root of 53 over 2. And x equals negative 5 halves minus the square root of 53 over 2. And so notice what we had here. We had 4 different zeros, and the degree of this original was a degree of 4, right? It turns out that's no accident, all right? So we'll kind of explore that more as we go along here. All right, so now what we're going to do is take what seems like a bit of a detour. We're actually going to go back to a much simpler type of a problem, and that is this x squared plus 1 equals 0. So let's say we were trying to find the zeros of the polynomial x squared plus 1. All right, now x squared plus 1 equals 0. You might say, all right, well, fine. How about we just solve it like this? So we get x squared equals negative 1. But if you stare at that for a second, you realize, okay, well, that doesn't really make sense. You don't square a number and get a negative, right? Because a negative times a negative is positive, and a positive times a positive is positive, of course. And so you might, at this point, say no solution. And you'd be right about that if you were talking about only real numbers. But what this equation leads us to is the idea of an imaginary number. Okay, so one way to think of what an imaginary number is all about is to say, well, you know what? So far, it hasn't made sense to say x squared equals negative 1, but what if it did? If it did, then the solution to this problem would be x equals plus or minus the square root of negative 1. Now, so far, this square root of negative 1 has always been nonsense, right? But what if we actually thought of it as not nonsense, at least for the time being? So what we do is we give it this name I for imaginary. And so what that does is it says that the solutions to this equation are plus or minus I. Okay? All right, so we'll talk a little bit more about that in a moment. Let's go down to example 3, though, and talk about this one specifically. So it wants us to solve this. X squared plus 4 equals 0. So if I kind of follow the pattern of that last problem, I might say x squared is negative 4. And then x would equal plus or minus the square root of negative 4, okay? Again, that doesn't really make sense. I'm not supposed to be able to take the square root of a negative. But if I go back to this idea that -1, if you take its square root, that gives you the imaginary number I, then I can make I appear here, right? I can say that -4 is the same as 4 times -1, but the square root of 4 is 2, leaving you only with the square root of -1, which gives you plus or minus 2i. Okay? Now, that's strange, right? What we're saying is that this polynomial x squared plus 4 does have two zeros, but they're imaginary zeros. Okay? Now hang with me for a second here, and let me go to our graph for a moment. Let's get rid of these. If I type in x squared plus 4, and I hit graph, you can look at this and see, okay, I don't see any zeros, right? I don't see anywhere I'm crossing the x-axis. So it definitely makes sense that that polynomial would have no real zeros that I can see here. So if there are such zeros, they'd have to be these things called imaginary zeros. All right. A little strange, but just hang with me. I guess the one comment that I would make before we go on and before you just dismiss this as, you know, mathematicians thinking of ways to make your life harder, these things called imaginary numbers actually come up in very real phenomena, especially in physics and chemistry and things like that. So one example is when you look at alternating current circuits. So I want you to just think about like the electricity running through buildings, okay? One component of an alternating current circuit might be a capacitor. And a capacitor has a property called impedance, which basically is saying, you know, how much does it impede the flow of current is kind of one way to look at that. Well, it turns out that the impedance of a capacitor needs imaginary numbers in order to be able to describe that measurement. Okay, so that's just one example. So very real thing, electricity running through our walls and things. There are imaginary numbers at play in all of that. Another example is just the movement of subatomic particles. So if you take an electron and if you want to have a function that's supposed to describe that electron's position within an atom, it turns out that you need an imaginary part to that function. I know it sounds strange, but you can't describe that position function of the electron without a real part and an imaginary part. So again, I don't think that that really takes the mystery away, but we have very good reason for studying these things called imaginary numbers. All right, now imaginary number is just a part of a larger concept that we call the complex number. All right, so a complex number is one of the form a plus bi. Okay, now the way I want you to think about this, and this is the way I think it makes the most sense, is we're all, you know, very used to number lines, right? So with a number line, right, you got 0 in the middle, 1, 2, 3, and so on, you know, -1, -2, -3, and no one's got any problems with that. So the idea with complex numbers is that you just take another number line and you put it vertical. Okay? And so what we do is, first of all, the regular number line that we already have, we call that the real number line. Oops, sorry, you can't see all that, right? There we go. Real number line. And then this vertical one we call the imaginary number line. And so up here, as you count up, this is the imaginary axis. So this would be I, 2i, 3i, and so on. Okay? And so just as an example, if I wanted to talk about the number 2 plus 3i, we would say 2 is the real part and 3 is the imaginary part, and so I'd go over 2, up 3. So it's like taking this idea of a number line and making it two-dimensional, and so the complex numbers are represented by points in this real axis combined with the imaginary axis in this space. Okay. All right, so we're not going to get really deeply into this, but so all the numbers that you're used to, right? Like if you say, okay, well, what about the number -5? Well, the number -5 is a complex number. It's just with plus 0 I. So it's just, -5 would be over here on the real axis. Okay. All right, so just a couple quick things. We're not going to spend a lot of time going into the detail of these things called complex numbers. One thing I do, before we jump into example 4, I almost forgot to mention is that this is an important realization here. I squared equals -1. Okay, why is that important? Well, it will have a lot of implications as far as simplifying things. So remember, I is the square root of -1. So if you squared that, then the square root should go away, right? So I squared would be -1. All right, so now with that, let's talk about how do we add things like complex numbers. Well, the nice thing is you just kind of use your familiar algebraic rules. So if I have the complex number 3 plus 4i and the complex number 7 minus 2i, then just like you might expect, you're going to combine like with like. So combine the real parts, combine the imaginary parts, and there you go. Right? So that's nice. As weird as these things are, at least they kind of follow logical rules, right? Same thing with subtraction, right? So if I say subtract this from that, that means I'm going to take 6 minus I, and I'm going to subtract off, and since there's two terms here, make sure you put it in parentheses. And just as if this were an x over here, you would be careful to distribute them negative through to both, right? So -1 times -3i is positive 3i. And then 6 minus 5 is 1. -1 plus 3 is 2i. All right. Just one more here. Okay, how does multiplication work? Okay, basically just like it works if that was an x in place of the I, with the added caveat that anytime we see an I squared, we can simplify it to be a -1. So in other words, when I see this, 5 plus 8i times 3 plus 2i, I'm just going to FOIL, right? First, so 5 times 3 is 15. Outside, 5 times 2i is 10i. Inside, 24i. And then last, that would be plus 16, but it would be I squared, right? Okay, so 16i squared. Remember, I squared is supposed to equal -1. So this is going to be 16 plus 10i plus 24i plus 16 times -1. Okay, oh, sorry, that's a 15, isn't it? 15, there we go. So it's 15 plus, we can combine these, 34i minus 16, and then I can combine my 15 and minus 16 to make -1 plus 34i. So you're just foiling, but if you see an I squared, you turn it into -1. Okay, so one of the things that we want to talk about then is in the context of finding the zeros of polynomials, right? How does looking at a particular type of polynomial tell me about what kind of zeros it's going to have or how many zeros it's going to have? Okay, so there's a couple of important theorems here. The first one, the fundamental theorem of algebra, says that every polynomial with complex coefficients has at least one complex zero. Okay, so even earlier when we were looking at x squared plus 4, we saw that the graph never crossed the x-axis. Well, this is saying, well, it definitely has at least one zero, even if it's complex, right? Even if it's not real where we can see it on the graph. And then, more importantly, the complete factorization theorem says this. If a polynomial has a certain degree, a degree n, then there exist n different complex numbers that you can factor this way, okay? Which means that each of those are zeros of the polynomial. Now, the only catch here is it's possible that there are repeats in this list, okay? So that's possible, but in other words, if you factor in multiplicity, if the highest degree term of a polynomial, say, is 5, because the biggest term is x to the 5th power, it is going to have 5 zeros. Now, some of them might be complex. Some of them could be repeats, okay? So you might have one where it's like, the zeros are 1, 4, and then the number 7, but the 7 shows up 3 different times, right? Or it has multiplicity 3. That could happen, okay? But there's got to be 5 when you factor in multiplicity. All right, so this is all very theoretical here. Let's put it into practice, okay? So it asks us to find all the zeros of this polynomial, x cubed plus x squared plus 4, all right? So we're going to start this just like we started our earlier one, which is let's use technology. But before we do, let's just make a note. That complete factorization theorem is basically telling me that there should be 3 zeros. Okay, 3 zeros, maybe one repeats itself, right? But basically there should be 3 zeros here. Might be complex, might be real, but we are expecting that many because this is the highest degree term. All right, so let's type this in. So we have x cubed plus x squared plus 4. All right, and so we'll graph that. Okay, looks like we have a good candidate right here. So let's find that 0. So go to the left, go to the right. X equals -2. And before we jump back to that page, let's just note it doesn't look like it crosses the x-axis anywhere else. So that probably means that this is our only real 0. So we'll just keep that in the back of our mind. All right, so we'll just make that comment. X equals -2 is a 0. So I can definitely say that my polynomial has the form x plus 2 times something, right? And to find that something, we do our synthetic division. Now remember what we learned when we learned about synthetic division is if a type of term is missing, make sure you put a placeholder. So I'll put 1 for 1x cubed, 1 for 1x squared, 0 because there is no x term, and then 4. All right, so don't forget about that. That's really important. All right, so we drop that 1 down, -2, add those to get -1, multiply to make 2, multiply to make -4, and then we get a remainder of 0. So we end up with x squared minus x plus 2. But once we get it down to that quadratic factor, just time for the quadratic formula, right? So we have x equals the opposite of -1 plus or minus the square root of -1 squared minus 4 times 1 times 2, all divided by 2 times 1. And when I clean this up, this is 1 plus or minus the square root. You get a -7 in there over 2, which would be 1/2 plus or minus, and then that, think of it like this, we have the square root of 7 times the square root of -1, just separating those out. over 2, which is 1/2 plus or minus, and then that square root of -1 becomes I. Square root of 7 over 2I. So those last two zeros are complex. So our zeros, just to list them all out here, are x equals -2, x equals 1/2 plus the square root of 7 over 2I, and x equals 1/2 minus the square root of 7 over 2I. So just like we were expecting, we do get 3 zeros. It's just that 2 of them are complex and you can't see them on the regular XY grid. All right, so give example 8 a try here and see if you find all of the zeros for it. All right, so of course we're going to start by using technology here. So 2x to the 4th minus 7x cubed plus 14x squared minus 15x plus 6. All right, so there's our function. So it certainly looks like there's only a single zero here, at least on the window that I'm looking at. All right, so let's go ahead and find this. All right, now again, don't be thrown off when this happens. 1.000006, it's just barely off because the algorithm just came out that way, right? At some point your calculator quits the algorithm that gets it to 0. So don't be alarmed by that. It's really x equals 1. Now, let's just, before we move on here, we can see that x equals 1 is a 0. And remember, right, what we learned about when zeros look like this, right? This thing looks like a quadratic at this 0, right? It comes down and rebounds up. So remembering what we learned from our previous standard, we know that that's a 0 of multiplicity 2, okay? So what I'm going to do is this, okay? I'm just going to say x equals 1 is a 0, and I'm going to go way down here, and I'm going to say, all right, my function, with the realization that, oops, that should be a -1, excuse me. With the realization that x equals 1 should be a 0 of multiplicity 2, that means that the factor x minus 1 should be to the second power. Okay, so I know that's eventually how it should turn out, times something, okay? But what I want to show you up here is even if you forgot that, that should not affect your ability to be able to come up with the correct answer here, okay? So, right, because what you would do is you would do your synthetic division. 2, -7, 14, -15, and 6. You do that synthetic division. We've done this a number of times now, so I'm going to do it nice and fast. Right? And so then that right there all by itself tells you that f of x is equal to x minus 1 times 2x cubed minus 5x squared plus 9x minus 6. Okay, now if you forgot about the whole multiplicity thing, then what you would do at that point is you would then plug this into the graphing calculator, right, to find another 0. And so even if you forgot about the multiplicity, I clear this out, and I put in 2x cubed minus 5x squared plus 9x minus 6. See, what happens is the 0 shows up again, right? So when it has a higher multiplicity, it just shows up again. No big deal, right? And so I would find this 0, and again, I'm saying, oh, x equals 1. That's another 0, right? So then I would just say, okay, x equals 1 is once again a 0. And so then you would again do the synthetic division here. And by the way, you have to do this synthetic division anyway because, in order to figure out what goes here, right? So even if you realize the multiplicity, you still got to go through the synthetic division twice. All right, so drop the 2. So that ends up giving us 2x squared minus 3x plus 6. All right, and then we can go ahead and use our quadratic formula. So this is x equals the opposite of negative 3 plus or minus the square root of negative 3 squared minus 4 times 2 times 6, all divided by 2 times 2. So this is going to be 3 plus or minus the square root of negative 39 over 4, or 3/4 plus or minus square root of 39 over 4, I. All right, so to list all our zeros, right, so we'd have x equals 1, and maybe just right here we'll put multiplicity 2, and then 3/4 plus the square root of 39 over 4, I, and 3/4 minus the square root of 39 over 4, I. And again, this one only has 3 zeros, right? And what were we expecting? This had a 4 up here, so we were expecting 4, but we did get 4, right? Because this one happened twice, right? So that's what we mean by saying it will have the same number of zeros as its degree as long as you're taking into account multiplicities.